Hello everyone, and welcome to my presentation. My name is Mathew. I am from the Department of Engineering Science and Mechanics, Virginia Polytechnic Institute and State University, Prague, USA. The title of my presentation is on phase field model to simulate crack initiation from fitting site in isotropic and anisotropic elastoplastic material. These are my co-authors and my advisor. So the background and challenges: collision represents the damaging electrochemical interaction between a susceptible metal and its surrounding, which results in the deterioration of the material strength and its longevity. In fields such as aerospace, biomedical, marine applications, structural components frequently encounter a dual challenge of enduring mechanical load alongside harsh environment conditions. In such scenario, the surrounding environment significantly contributes to the failure and fracture mechanism of these components. So first, we introduced the methodology we adopted in this study. We introduced a phase field variable to differentiate the solid and the electrolyte phase, and we described the interface evolution of a complex shape. Then we built in a thermodynamic consistent manner, and lastly, completely extended it for multi-physics system. So the key features and innovation of this work is that we use a multi-physics phase field model to simulate the crack initiation from fitting site under the combination of chemical and mechanical field. Then the peak to crack transition is simulated by utilizing the film nurture dissolution mechanism and nonlinear dependence of the interface kinetic on the electrochemical driving force. Then the mechanical behavior was used to model the isotropic and anisotropic materials. So first we define the free energy functional as F, which is the sum of the integral of F bulk and F int. The F bulk is the chemical bulk contribution and F int is the interfacial contribution, and the evolution of the non-conserved order parameter field eta follows in this expression, where L is the kinetic coefficient which represents the mobility of the interface. Then the collision model, we define our collision model with this equation with the energy functional F as the integral of F bulk and F int, and we define the F bulk as the sum of the interpolation function H and the double well free energy function G. And at the same time, the F int is defined as interfacial or gradient term, which is given in this expression also. And we coupled it with nonlinear dependence of energy driving force, this time to the collision model. And the next, we define the elastoplastic model. First one is isotropic model with J2 plasticity. So we define the mechanical strain as the sum of the elastic strain and the plastic strain. Then from there, we calculate our trial stress using this expression, and also our effective plastic strain using the trial stress we got from the second equation. Then elastic model for anisotropic material. Then here first F is the gradient deformation or deformation gradient, where we decompose it into elastic and the plastic part, and S is the circumferential curve tensor. This dissolve shear stress, this is tau, and this equation is for slip system strength. Then we couple the collision and the mechanical models together using this equation, the passive and the effective plastic strain. Then this one is the plastic strain to initiate the passive film rupture. Then the second equation, the gamma sub SCC, is the accumulative slip, which is the accumulative slip that requires to damage the film rupture. Then also we account for the influence of phase field in the moment balance equation, where the divergence of the stress field is equals to 0. And we also introduce a small number psi, so that we can ensure that our system is stable. Then the overall governing equation of this simulation is two. The first one is the electrochemical model, while the second one is the chemical model. The combination of the two, we implemented the two equations in the open source MOOS, which is Multiphysics Object-Oriented Simulation Environment Framework. And we use the Virginia Tech Advanced Research Computing. And we also use adaptive mesh and adaptive time step size. So the first problem we solve is our benchmark problem, which is pencil electrode. So we define our domain as this, where the length is 128 micrometer and the height is 32 micrometer. And the red portion is our solid domain, while the blue portion is our solution or electrolyte. The psi, the phase field parameter for the solid domain, is defined as 1. We are here for the electrolyte or solution is defined to be 0. And the normal boundary condition is introduced along the domain, which is the psi over t equals to 0. And this is our material parameter that was used for simulation. Shows the result of evolution of phase field variable at different time. As we can see, when the peaks start to grow at equals to 232.3 seconds, the electrolyte is consuming more of the metal, and as time goes up, it consumes more of the metal and more of the metal as time goes, as you can see in the last diagram. So this represents the phase field and base field net at eta equals 100 millivolts. That is the energy potential for the simulation. So the figure shows the variation of peak depth and time. The blue portion shows for the peak depth, and the red portion is the current density versus time. We also showed the plot of nonlinear dependence of an interface velocity of the overpotential. The relationship between the velocity and the overpotential is given in this plot. Then we modeled the crack initiation from pit in isotropic material in a 2D plane, where this is the domain. We introduce a small semicircular pit and fill it with an electrolyte or solution at the top. As you can see, the radius of this pit is 0.5, and the phase field at t equals to 0, that is the initial boundary condition, is 0. And the metal itself, the other regions, phase field at t equals to 0 is 1. And the boundary condition, this is constrained in the left, and it's also constrained at the bottom. The top is left stress-free, and we introduce a strain rate of 2.5 exponential minus 8 per seconds. So this is our initial boundary setup. And this represents our material parameters for the simulation, both the collision material parameters and the mechanical parameters as well. So as you can see, the result of this simulation goes like this. So you can see how the pit grows in this metal or in this solid from the semicircular pit. So at different times, the pit grows, and you can see the adaptive mesh that we introduced to capture the evolution of the surface. Massive stress field, also the corresponding massive stress field. Yeah. The figure here shows the evolution of phase field for different T and for different film Lorentz values. Like the first row shows when there's no mechanical load. As you can see, we only have only PT load because there's no mechanical load at the applied. Then in the second row, we only apply the film Lorentz value of 0.05, and the third one, film Lorentz of 0.1, and in the fourth one, film Lorentz of 0.2. So we can see that when we apply big film Lorentz value, then we're also going to have a very big pit, and also big the crack propagation will also widened and increased as we compare to 0.05. So this one is very narrow, and but this one is the biggest in terms of pit size and the crack size. as well. We use film distribution mechanism, and it's considered by enhancing the interface kinetic when the mechanical strength is sufficient to rupture the surface of the metal. And we selected model parameters we studied to understand the peak to crack transition in 2D and 3D in both isotropic and anisotropic material. Then in all conditions, a peak to crack transition was observed, and the crack transition could strongly depend on crystal orientation and deviate from perpendicular to the applied loading direction in material isotropic mechanical behaviors. So my acknowledgement goes to Office of the Naval Research and the National Science Foundation for their support of this research, and also Advanced Research Computing and Virginia Tech, and our collaborator, Professor Albert and Professor Vijay. Thank you.